Okay, so can everybody see this? Well, this will be nice. All right, so I just want to clarify this, this last problem here. So let me just grab this. Okay, so you can see that. Okay, this is the first time I've ever done this. Use this iPad in an in-person lecture, so I might need a few times to get the hang of this and feel comfortable about it. But anyway, so starting off, okay, so we're recording. Okay, recording, and that's up, and then I got the mic on, right? Okay, all right. So we have here, so does this work? Good. So you understand this is a cylindrical shaft that is pulled through this bearing. So this is like a cylindrical opening, right? And it's pulled through by some imposed force, constant P, okay? And we are given the value of P. And then this diameter of the shaft is 30 millimeter, and it slides along a bearing of this length, okay? And at some constant speed. So we have a constant speed of the shaft, and then this gap between the shaft and bearing. So there's this small gap, very small, as you can see, is... So let me, so something like this. So looking at it from the side, I should have used that feature that I can draw perfect circles, but for now. Okay, so the lubricant is in here, right? And actually, let me undo that. Oops. Oh, is there a redo? Redo. Oh, I wish I could do this on the blackboard, but then if I get this working, maybe I could just continue with this. So, so actually, I didn't draw. This is not drawn to scale, but in general, you know, we can consider this whole thing. So here's the shaft, and then that gap is very thin. So basically, the way one does the overall analysis is that this radius of curvature, or it could be here, is much larger than this gap width. We can call it W. So that assumption leads to the assumption that this. So if we look at this, that the velocity profile, sorry, it's straight, right? The velocity profile can be assumed linear. Okay, so it's a very thin gap and a large cylindrical surface, but it's very, you know, it's very large so that the gap, essentially the fluid sees something that's sort of flat. Okay, so that's why it's simplified like that. If it wasn't, and we can, you know, maybe consider a flow like this in Chapter 6, you have flow through an annulus, and you know, that's a whole different thing that has to consider the curvature of the problem. All right, so then this you can do this one of either two ways. So let me. Okay, so you could unwrap it and consider, so actually, sorry, this is a different problem that I had in mind. Forget this shape. Now, looking at it from the side, sorry about that, don't just erase that. It's this view where the this surface, the shaft, is moving at the velocity, let's call it big U, Okay? And then this bearing surface, the top surface here, okay, is stationary. So here, little u equal big U, sorry, 0. Okay, so here, little u equals 0, and here, little u equal big U, if we consider u in the x direction. Okay, now, because this could be considered just a flat surface going in this direction, we could do this problem by just assuming xy 2D flow and considering this is x and a local coordinate, this is y. Okay? Then if this is the gap width, maybe W is not the best. Let's call it H. Okay, so this is, oh, I never wrote it down. Okay. Then you could, now, a linear profile that is consistent with these boundary conditions looks like this. The other direction, this other sketch that I had previously over here, forget that. Okay, so this would be the appropriate velocity profile, linear, okay, where at the shaft surface, it's big U, and then at the bearing surface, it's 0, and then it's across some vertical height h. So you could assume x, y, and then tau is equal to mu du dy. Okay, so, and that's what we discussed. Okay, so you could, because we're sort of considering that it's essentially a flat surface, consider this local coordinate y, and then just use the previous expression and that we discussed in class. And then you could figure out u as a function of y for this very simple linear problem. Okay? Yeah?
Is h 1 millimeter? Is it 1 millimeter total? So that's half the
So
millimeter.
h is the gap width or height. Okay? And this is just a cross, this is just showing a cross section. So if we just looked at a plane here, if we cut it, we would see this view. Okay? Now, in reality, this is cylindrical, so one could also, let me do this blue, if you would like. So here's the shaft, right? So this is velocity big U, and then here is the bearing surface. So that is the fixed, U equals 0. Okay, and then we have this linear profile in the fluid. Now, if one prefers, you could do this with the r coordinate. Okay, so the coordinate would be x along the shaft, and then at the center line of the shaft would be the origin, and then r radially outward. Okay, then you could determine u as a function of r for this particular problem. So the boundary conditions that have to be met is at r equal d over 2, d the diameter of the shaft, u of x is equal to big U, and at r equal d over 2 plus h, the bearing surface, u of x is equal to 0, right? And then in cylindrical coordinates, tau, and it would be rx, so the first subscript is indicates the area. So the shear stress acts on, so the area normal is in the R direction. So the surface that the shear stress acts on truly is cylindrical, right? It's this cylinder, the area here at this location would be the cylinder here with at diameter d over 2, and then the length 50 millimeter. The outward normal of that surface is in the R direction. And then the shear stress corresponding force acts in the X direction. Okay? And the shear stress, similar to this, remember this one is tau yx, is proportional to the gradient of the velocity. So it actually looks similar. It would be mu du in the X direction dr. So it's comparable to this, the one in the expression in Cartesian coordinates. And so if you want to just formally do it in cylindrical coordinates, you can. In either case, you would get the same result because the shear stress is proportional to the gradient. And make sure that you evaluate u of x as a function of r such that it has a negative slope, right? With increasing r, the u decreases. Here, with increasing y, the u decreases, and you're just taking the slope. So in either case, it works out to be the same, okay, and negative. And then another clarification, which is very basic, and I'm sure that all of you certainly have this worked out, but sometimes I just want to emphasize the basics because once things get more complex, you have to rely on your knowledge of the basics and make it, that's where you start from, right? And make sure those are exact, okay? If you don't have the basics exactly as it should be precise, then you're just immediately on shaky grounds. So for this particular problem, when this shaft is pulled to the right and moving to the right, there's going to be a counteracting resistance force, a shear force due to the lubricant acting on this surface of the shaft to the left. So it's appropriate in your analysis to draw a free body diagram on your shaft. So there's an imposed constant force P, okay? And due to the lubricant, you're going to have a shear force, let's call it F tau, acting to the left. Was there a question? Yes?
Yeah, I was actually going to ask about tau. So we're given the force put on the shaft, so I assume we can actually calculate that shear stress that it feels?
Yes.
So my question is it just F over A being the area of the shaft that is inside of the...
Actually, that's why I was going to go over this. And this F tau, so formally F tau would be the integral of tau, the shear stress, which is force per unit area, and you integrate over the area, okay? In this case, the shear stress over the area, over this entire cylindrical area of the shaft, is constant, okay? So then this would be pulled out, and it's just tau times the area of the shaft. Okay? Now, when you evaluate this, it's going to be negative. Okay? But this F here that I evaluated, you could think of it as the magnitude. So you would take the magnitude of tau, okay, multiply it by the area. Now, the overall analysis is based on Newton's second law. You better have Newton's second law in this problem as a governing equation. Okay? Start from the general. And then a vector equation, you apply the component equation. So in this case, it would be, oops, this thing's a little slippery, so sometimes the line just keeps going. So the component of the Newton's second law is in the x direction, okay? And you apply it to the shaft. So free body diagram indicating the forces and their direction on that diagram, right? And then constant speed, right? This was constant speed, so there's no acceleration. So 0. Some people like to write some of the forces, okay? And now when you evaluate this, what do? You look and consider the forces acting, okay? So there's P in the positive x direction, so that's plus P. The magnitude of this was given as, what, 2 newtons? Okay. So positive P. Now this F tau, okay, we know how to evaluate the magnitude. It's the shear stress times the area. That should be some positive value if we're considering this to be a magnitude. Its direction would be indicated when you evaluate that term in this equation. So this negative sign here accounts for the direction of tau, which we know just physically, it's a shear force acting on the shaft, right, opposing its motion. And then that's equal to 0. So then you just simply get, P is equal to tau A as you want to, right? The problem is some people immediately start from here. Okay, and so you're missing out on some very basic stuff, which you guys, for such a simple problem, can do this in your head. But when things get more complex, you want to start from the basics. You want to start from the beginning and clearly indicate a diagram, consider all the forces, a diagram of the thing that you are analyzing, right? And then the governing equation, and then you apply it to this particular problem, and then come up with an equation which you can then solve for the unknown. So the unknown viscosity would be in this tau, right? Which is mu du dy or du x dr. Either case, you're going to get the same gradient and you'll get the same tau magnitude. Okay? So I just want to go over the basics. This is so simple. The only thing I didn't do is give you, I forgot that this is cylindrical coordinates and you guys don't have this expression, but it's basically the same in this particular problem, okay? And then you can go from there. But I think it's of value to sort of emphasize the basics, because once things get more complicated, some of you may be searching in the textbook for that final equation to plug and chug. No. I want to see and make sure you understand the basic analysis, starting from general governing equations, okay? All right, so did I spend the whole class period on the homework assignment? But at least now you should be able to do the whole homework assignment. This particular problem, the fourth, problem number 4, is a very important problem for you to understand, but this also, all of this also we're going to return to in chapter 6, differential analysis. But just this basic idea of shear stress and the corresponding force. And just keep in mind what we're talking about in terms of shear stress. First of all, it occurs when you have relative motion. Okay? So here in the fluid, you have a varying velocity. So you have relative motion. So whether it's shear stress at the interface between fluid and solid or within the fluid, if you have relative motion, so here within the fluid, there's relative motion between fluid particles. So a fluid particle here, because it's up, the neighbor above it is going faster, is going to experience that shear stress to the right. Meanwhile, if that fluid element, okay, looking at the lower surface, that fluid element is going so the lower neighbor is going slower. So that relative motion is going to cause the shear force in the opposing direction. Okay? And that's what this equation describes. Okay? And then we had, in the previous, last Friday, we had this, we considered the shear stress on an upper surface and a lower surface, and considered the sign directions in terms of the shear stress, the direction of the forces, all of that last time. Okay, but it's all, what I want you to understand is how the physics is described precisely by the math. Okay, and so all throughout, we're going to, that's going to be the case. Okay, and in fluid mechanics, it's so nice how well the math describes the physics. Okay, let's move on. I think today, since I spent so much time on the homework assignment, I'm just going to refer to the notes, and I think we can just kind of go through the material a little faster if we just, copy. If we just refer to the notes. So today is the 18th. Okay, and so, we're going to start fluid statics. Oh, there was one more. I do want to make one more comment before we do that. So first, one more comment about non-Newtonian fluids. So it was the last two slides from the last week's lecture, and then start the topic of fluid statics. And the first subtopic within fluid statics is, the general description of pressure variation in a fluid. So we'll develop the governing equations, and then we can apply it to an incompressible fluid. That is a fluid where we can assume the density is constant, and then we can evaluate how the pressure varies through that fluid. And then the more general case where it's a compressible fluid, for example, air, where the density may vary within the fluid. Okay? And this particular example, well, actually both of them, will allow us to evaluate, say, the pressure variation in the atmosphere. And we know as you go up in the atmosphere, the temperature may vary, okay, and the pressure varies, and so the density may vary. And so we can use our governing equation to evaluate the pressure variation through what is referred to as standard atmosphere. Okay, and that's basically how the values in the table for standard atmosphere, which is a table in your appendix. So at a given elevation, it lists pressure, temperature, density for some standard atmosphere corresponding to some mid-latitude, just sort of an average over all seasons and day reference if you want to do analysis, for example, of flow over an aircraft flying in the atmosphere. Okay, but that's one application. Okay, but this is a very important base for the discussion of fluid statics. And then that leads to discussion of pressure measurement, and in particular manometry. And then once we have a pressure variation, we can, if there is a surface or an object that is submerged in a fluid that has a pressure variation, one objective is to evaluate the force on the submerged surface. So if you've got some object in the ocean and it's at some depth, then we can evaluate the the force. So that's kind of where we're going. Maybe today we can just get at least maybe look at the pressure variation, the governing equation, and then apply it to an incompressible fluid. Okay? Okay, so then let me do this. Okay, is that better? All right. I'm going to have to figure out a better way of doing this. All right, so this slide. Oh, this slide is, okay. I told you that I wanted to quickly, 1.1, okay, quickly comment on non-Newtonian fluid. Okay, so this is just the last part of last week's lecture. So if the shear stress is proportional to the rate of deformation, as we discussed last time, then we have and then the proportionality constant is not a function of the shear stress or rate of deformation. That is, this property that we referred to as viscosity does not depend on the shear stress or the rate of deformation. It's a Newtonian fluid. And most common fluids are Newtonian fluids, like oil, water, or air. So mathematically, if we plot the shear stress as a function of the rate of deformation, then mu would be constant. So we would have a constant slope. And the slope would indicate the viscosity. So oil is more viscous than water, more viscous than air. Okay? And as I mentioned, for our class, we're going to always assume Newtonian fluid. Okay? But there are non-Newtonian fluids. That is, these are fluids in which this proportionality variable may depend on the imposed shear stress or rate of deformation. Okay? And so if we consider shear stress as a function of rate of deformation, and here we have our Newtonian fluid. Okay? So viscosity is constant with respect to the imposed shear stress. But there are other types of fluids. So for example, the so-called shear thickening fluid, where for low values of shear stress, okay, then you have some behavior. But if you increase the shear stress, okay, then you have an increase in the resistance to the motion. And so one example would be cornstarch a mixture of cornstarch and water behaves like this, or quicksand. Shear thickening versus shear thinning, where you have a greater resistance to motion for low shear stress, but for a greater shear stress, that resistance of motion diminishes. So latex paint. So if you put your paintbrush in the paint, okay, then the paint will not flow off so easily, okay? But then if you apply it on the wall, okay, you're moving your paintbrush and you're imposing a greater shear stress, okay, then it flows more easily, as you would want the paint to do when you're painting, okay? So that would be shear thinning. Oops. I don't want to do this because this is my permanent. And then some fluids are actually quite really sort of different. And some fluids or substances may actually behave more like a solid, which it doesn't flow for low values of shear stress, but then there's a yield stress beyond which then it'll start flowing. And these are referred to as Bingham plastics, and a common example is toothpaste. So the stuff is in a tube, and if you put the tube upside down, it doesn't flow out like water would if it was in the tube, right? But then you have to press and squeeze the tube. That causes a shear stress to be imposed, and then it starts flowing out. Okay, this whole study of this behavior, different behavior of fluids, is called rheology. That's a whole different field of science that we're not going to be involved with, but just be familiar with the fact that there are non-Newtonian fluids that may be described by some apparent viscosity, okay? And you may encounter someday, and then you have to do things a little differently when you evaluate shear stress. We're always going to assume Newtonian fluid in 101A, okay? All right, so that finishes last week's discussion. All right, and then I just wanted to make a comment that in fluid mechanics, as I mentioned last week, the very basic analysis of fluid dynamics is going to involve applying these basic laws of physics, conservation of mass, conservation of momentum, which is essentially Newton's second law. And in general, the objective may be to evaluate and determine the flow, which involves the velocity distribution, the pressure distribution in both space and time. So this would be like a general objective. So if you want to analyze a flow with all the details, okay, that would be it. Now, first we're going to consider the simple case where we have the fluid not moving. Okay, so if it's not accelerating, then this would be 0, and there's just a force balance. And if it's not moving, essentially conservation of mass boils down to the mass is constant. And so that's our starting point. And so if it's not moving, the velocity is 0, but there may be a pressure distribution. Okay? And so we're going to look at that. But that may give you some idea of what's to come for the general case, where we not only evaluate a pressure distribution, but a corresponding velocity distribution, and we have to bring in conservation of mass, and everything is moving and changing. It could be in both 3D space and time, and that's when things get very complex. So let's just first start from the simplest case where nothing is moving, but there is a pressure variation. Okay? So that's fluid statics. The hydrostatic condition, no motion, fluid at rest, is V is 0. But within this chapter, we can also consider the basic problem of rigid body motion. So for fluid like this, where you may have some body of fluid, and it's moving, but it all moves at once. Okay? So, for example, this is the classic problem would be if you have an aquarium, a tank of water that you want to transport in your car. And so, you put it in the back seat, and then you move, and then you can also accelerate in your car, right? And we can analyze what's going to happen to the water in your tank when you accelerate by assuming that the water in the tank moves as a rigid body. So it all moves at once. The underlying assumption, so we can handle this problem very simply in this chapter. The underlying assumption is there's no relative motion and therefore no shear. So in chapter 2, no shear stress. But there is pressure, the normal stress in the fluid, and the corresponding force. Okay, so that's what we're going to consider. And so we're going to investigate the pressure distribution in a stationary fluid or a fluid that may accelerate but moves as a whole. And then two important applications, well, 3 important applications, as I mentioned: pressure distribution in the atmosphere or in a fluid, and that leads to pressure measurement, for example, manometers, and then the evaluation of forces on submerged objects or surfaces. So those 3 are the main subjects. There's a couple other ones that we'll discuss as well, but those are the 3 objectives of this chapter. Okay, so I got 7 minutes to derive the basic equation for the pressure field. Consider a fluid element, a cubical fluid element, surrounding a point O, that is located in Cartesian coordinates x, y, z, okay, at point x, y, z. Okay? And this cubical element has sides, so it's an infinitesimal size, has sides delta x, delta y, delta z, okay? And we have our Cartesian coordinate system, and with unit vectors I, j, k to indicate the three directions. And we can consider an infinitesimal force, delta F, or the infinitesimal resultant force on this fluid element, okay? And that's, we can consider the basic equation by Newton's second law, equal delta M. So this infinitesimal mass associated with the fluid element times the acceleration of the fluid element. Okay, so this is just Newton's second law applied to our infinitesimal fluid element. And it's a vector equation. So this delta F, the resultant force on the fluid element, is a vector. So there would be an x, y, and z component in the three directions. Now, in general, there are two types of forces. There are body forces. So we indicate it by F sub b. Okay? And there are various body forces that act on the object as a whole over the entire volume. But the force due to the external force, gravity, is the one that we're going to consider as the main gravity body force. There are others, magnetic force, as an example. Those are special effects that we're not going to consider. So the main and only body force is essentially the weight, and due to the gravitational acceleration, g. Okay? There are also surface forces, and the surface force that acts over the surfaces of the fluid element is going to be due to pressure. Okay? So that's a main force to consider. So this resultant or net force can be broken up into the body force and the surface force. Okay, so now if we consider the forces acting, you can see that there's a body force here acting through the center of mass. Okay, so that's this delta FB. And then on each of the surfaces of the fluid element, then we have why doesn't it shut up? All right. Now, the surface force is going to be due to pressure. And we discussed force associated with pressure last week, right? And so the differential force due to pressure is given by minus P dA. Okay? So the pressure acting on the surface, okay? And here's the differential area, dA. And the force is in the opposite direction to the area outward normal. Okay? So this dA is a vector in the direction of the outward normal. And remember, the negative sign there is because the pressure force always acts towards the surface. So here I have sketched the force due to the pressure acting over each of the sides. Okay, so the pressure, so of course each of these forces is acting towards the surfaces, and the pressure would be some average pressure at that location. Okay, so if the point O, the center, is at coordinate x, y, z, okay, then here we could consider the resultant force acting at the center at that same x, y coordinate, but at a location z plus delta z over 2 above point O, right? So that's why I wrote P evaluated at z plus delta z over 2 times delta AZ, which would be this area. So delta AZ, because this area has its normal in the z direction. Okay? Now here is the force acting on this area, the side area. So we have the pressure averaged at this location, which is a location that is, so if this point O is at a coordinate y, this area has the same xz location, but is at the coordinate y plus delta y over 2. Okay? So that's how the forces associated with the pressure work. This delta AY, by the way, is delta x times delta z, simply. So we can consider each of these 6 forces. And actually, I have what I just explained kind of indicated here in terms of the forces due to the pressure acting on the 2 sides and the variation in the y direction. Okay, now this net surface force then could be written like this. So the surface force acting in the x direction, the net, okay, and then the net surface force in the y, the net surface force in the z. So let's just consider how this is evaluated. So this would be the surface force in the y direction. So that would be this in the positive y minus this acting in the negative y. So that's this minus this, okay? This minus this. Now, to evaluate this value of the pressure, okay, we just do a Taylor series expansion about this point. Okay, so I've just written here Taylor series expansion for some function where we know the value of the function at x, and we're going to expand, and we want to evaluate at x plus delta x. So recall that this is Taylor series expansion. This is the first derivative of f, the second derivative, and so on. Now, these are higher order terms, which we're going to neglect, so we can evaluate this pressure at this location using Taylor series expansion, these terms. Okay? So if we do that, so P at y minus delta y over 2, which is going to be on this side of y, so a distance y minus delta y over 2 here, can be expressed as P at xyz, which is at the point O, plus partial P partial y, that's this, times the delta x. The delta, the distance here is going to be this distance, which is the delta y over 2, okay? And we're going minus in the minus y direction. So we can evaluate each of these pressures using the Taylor series expansion. So we get P at y minus delta y over 2, P at y plus delta y over 2, okay? And we could substitute it in here and here, and to get the delta f s sub y, okay? The area y is delta x delta z, same for both terms. And you can see that the leading order P cancels, P and minus P cancel, and then you have 1/2 minus partial P partial y in both terms, and so they add up to be minus partial P partial y, okay? And then this delta y multiplied by delta x delta z gives you this, which actually happens to be the incremental volume of the fluid element. So we have that first term in the y direction, and you can do correspondingly in the 2 other directions, and then substitute in the net resultant surface force, and combining you get what is the pressure gradient, or the del operating on the pressure, del operator operating on pressure. So the net surface force is proportional to the pressure gradient, okay, times this incremental volume. Sorry for running over, but that's the governing equation basically. Okay, so we'll continue Friday.